So today we will be covering the lab number 8. And by the way, I was checking your exams and I found that most of you had not performed well in the lab part. So was it very difficult for you? Particularly the second question of the lab part, like question number 9. So there were very few students who attempted that one. So I don't know because I had given you all the objective questions, multiple choice questions, and yeah, and that's why I had also advised you to at least watch the videos because I had covered everything in the lectures. So if you have any question or something related to the exam, the if it's very difficult, then please let me know. I'll solve it for you. And if you have any question in the previous lab as well, so you can ask me and then I can answer you for that too. Okay. Okay. So do you have any question now? Okay. So I think I shall start with the lecture. So today lab is the continuation of the previous lab, and this is the part 2 of the simplified LTE system. So in today's lab, we will be covering the uh, block interleaver. I'll explain this thing in detail to you, and then I'll also explain you what is the modulation. And since we had already covered the BPSK modulation, we will see it once again with the LTE system, and also we will cover the one of the QAM and advanced modulation, which is 4 QAM. There are different type of QAM, so 4, 16, 32. I'll also explain you what the difference is in between them. So this is the block diagram. So some of we have covered the first 3 blocks we have covered in the previous lab. So the first one was the random bit generation. We had generated almost 4 kilo of bits, random bits, and then uh, I have done some modification in the code to make it more easier and more readable for you. So I'll show you again from the start, and then I'll reshape it so that I can say that they are 4 times of 1 kilobits. So it will be 4 cross 102 for matrix. So the each row will show you 1 kilobit. So we in fact generated 4 kilobit, but we want to express it in 4 rows, and each row contains 1 kilobit. Then we will apply it to the Hamming coding, and the Hamming coding will apply the FAC coding, forward error correction coding, which is the channel encoding technique, and we saw it in more detail in previous lab. So if you have any confusion with this thing, you can please watch the previous video. And then it will extend it to the 7 kilobit. Why 7 kilobit? Because it will add the parity bit as well. So the parity, as we saw, we calculated the parity from the given message signal. So if you have 4 bit of the message, then there were 3 parity bits required. So it's not just random. If you have like 4 bit of the message and you just randomly put like 3 bit or 2 bit or 1 bit parity, you have to calculate it properly, that I had shown you in previous lab for Hamming coding only. And then that parity has to be added there. That parity will be generated automatically by the Hamming coding. Now, in today's lab, we will be covering two more blocks. One is the block interleaver, and the other one is the modulation part. So, the block interleaver, I'll explain you in a while in more detail. Uh, it takes the data from the Hamming coding, so there might be still something to be done with the data, so that to avoid the error uh, in the communication model. To reduce at the end, there is something which is called the bit error rate, and to reduce the bit error rate, you have to make the data more and more immune to noise. So to make the data more and more immune to noise, you have to do some processes. So firstly, we did the FAC coding, which is the channel coding, but that was not sufficient. So we will do one more thing, which is the black interleaver. And after that, we will cover the modulation part. So in today's lab, I'll show you what is the BPSK modulation and other types of modulation, what is the symbol, what is the symbol interval, and all the things related to the modulations. So then this block will be proceeded further to the next blocks in the next labs. So firstly, coming to the block interleaver. So I'll come back to the slide, and let's go to the drawing page first. I'll explain you what the block interleaver is, and then we will come back and I'll explain. Then you will easily understand this one. It's now too early for you to digest all this stuff. So I'll switch to my other screen. So the black interleaver. Firstly, as I told you, we generated the bits. So that was the mm, bits generation. And the bits were randomly generated. And we had created up to 4 kilo of bits. So the 4 kilo bits were then reshaped, and they were reshaped in such a way that in 4 columns we created 4 columns, and each columns contains 1 kilobit of the bit. So 1 kilobit was here, the other kilobit was here, 1 kilobit was here, and the 1 kilobit was here. So we didn't do anything extra, but just we expressed the 4 kilobit which was in the single vector. Here the 4 kilobits were in the single vector like this, right? So all were in the 4k bit were like this in the single vector, but we converted into 4 rows, and each row will now contain the 1 kb. So this will be easier for the further processes. And then each kilobit, by kilobit block, we gave it to the Hamming coding FEC coder, and FEC coder processed it, and then it will give it to the block interleaver, which I will call just a BI. So what is the block interleaver? So if you have seen the previous block diagram clearly, there I had mentioned like it is 32 by 32 black interleaver. Why 32 by 32? Because 32 by 32 is equal to 1024, and since each of the column here contains 1024, so it will take 1024 column here, and then it will express it in the form of 32 by 32. How? It means 32 by 32 bit means that it will express the first 32 bit like this in the first row, then the next 32 bit like this in this next row, and up to the 32nd row it will finally express all the number of bits. So all the 1024 bits that were in the first row, it will comes and it will be aligned in the 32 plus 32 bit block interleaver. So this is the block interleaver. Now, uh, how the data is coming in and how the data is going out, and why is this thing required, like is why don't we just simply bypass this block, we just don't need, and just give it to the modulation? Why do we need it? So to understand this thing, we have the mm, if you remember the, I think the first lecture on this LTE, I had explained you some channel gain, right? So it was, I had explained you something like that. So the behavior of the channel changes with respect to time. So the channel is not good always. Why it is not good? Because it depends on the your environment. If your environment is very clean, if your transmitter here and your receiver here, they are in line of sight, which means that they can see each other directly. In that case, and then there is no one moving, and there is not much scatters in this environment, then in that case the channel will be quite flat. It will be experiencing very low fading. But when there is some scatters, for example, there are rooms, buildings, people moving, cars moving, different type of stuff are there, then because of those scatters or those uh, phenomena, those interferers, they are, the signal is reflected off those stuff, and then it is received at the receiver like this. And when they are added here, they are not added at the same phase, they are added with different phases because of different delays, and that delays and those phases give rise to fading. So sometimes the fading is very sharp like this, and sometimes the fading is not so sharp. So this kind of fading is called deep fading. So if you, then I told you that when you are sending your signal in frequency domain, you are in the LTE, you are sending it through the subcarriers. And the subcarriers are the small chunks, the small bin, which carries your data, and that data is transported from the source to destination. So if your bin is allocated, for example, here, and then this fading occur, it means that this bin has been corrupted. And then again the data here, the data is almost fine because this portion is flat, this is flat, this is also somehow flat, but still there is some noise. But if you look at this portion, for example this portion, there you can see that this is not okay, this one portion is not okay. If there is some subcarrier here, again this portion is not okay because there is this fading. So this kind of fading, when you have, when your channel is experiencing this kind of fading, then, and it means that it is corrupting the data here, it will corrupt your data. So if you are sending, for example, 101 bit here, and then there is a fading, this data may be corrupted to maybe 011 or any 100 or anything. So to then again also this data may be corrupted here, and this data may be corrupted here, and such kind of error is called burst error, burst error at transmission. So what if you are sending your data like this? Now let's come back to this picture again, this one. So you are transmitting your data, and your transmitted data is sequentially, it is in the same sequence as it is. For example, your first 32 bits, then followed by the next 32 bits, then followed by the next 32 bits, up to the last 32 bits. So if this fading happen, this fading will be happening in this case if you are not doing the interleaving. For example, I'm not talking about, I'm currently considering this is null, this is not there. So if you are not doing the interleaving, and for example the first 32 bits are there and the fading occurred here, for example the fading occurred here, so let's say there are 4 or 5 bits that are affected by that kind of fading. So it means that the data corrupted with consecutive bits, the bits were located very close, they were back to back bits, and because of the fading all the bits were corrupted, all those bits were corrupted. So we want to avoid this thing because if this portion of the data is corrupted, for example, then it means that your signal, you are sending the information and part of the information is corrupted and the receiver will unable to recover that. And as I have told you, the Hamming coding was capable to correct only one error, one bit per sequence. So if you have more bit per sequence, that means that the Hamming coding is unable to correct that. For that, you have to do something more. So why we do need the black interleaving? Now this thing comes in picture. So the black interleaving, as I told you, the first 32 bit are here, then the next 32, and then this one. We enter the data in the row form. So the 32 bits are coming here, then the next 32 are coming here. So the data is input in a row form. So it is input is in a row form, and the data is taken in a column form. I think I should do it in the clear picture. So this is the black interleaver, black interleaver, and I have, for example, 32 cross 32 black, and then the row form, the data is input, the data from the FEC is coming here. For example, the Hamming coding data is coming here, and the Hamming code coming, the first 32 bits will come here. So the data input is in the form of row, then the next 32 bits are coming here, then the next 32 bits are coming here, and so forth. So all the data is coming is in the form of row, but at the output the data is taken as a column. So firstly the first column will be taken, then the next column will be taken, then the third column will be taken, and so far up to the last column. So the data is uh, extracted from the columns. So what is the benefit now? When your data is taken from the columns, and let's say the error occurred here, that one error, this error, this error is now occurred at, sorry, I, this error is occurred at this portion, for example, this portion. So the data again will be looking like that, but it is column wise data. So if that error is occurred here, it will not be that much worse than the previous case. Why? Because this is the 32nd, because let's say that the 32, the 33rd number bit is corrupted. Then for example, up to the 64 bits are here, then the 65th bit is corrupted. So they are not back to back bits, which means that even if they are corrupted, they will not be back to back bets and they will not affect each other. So these bets are not so harmful. And even if they are corrupted, it's okay. So that's why we need the black interleaver. And the black interleaver kind of permute your data, which is the data which is coming in the row wise as an output, and it is taken as a column wise. So did you understand why we need it? Why the bit interleaver is required? So that is the main concept for the bit interleaver. So this was the bit interleaver, and then we will. I will also explain you the modulation part. So for the modulation, your input of the all the data is coming in the form of 0 1 0 1, because it's the digital data. So the data is in the form of bit stream or in the digital form, but you cannot send the bit stream or the digital form over the medium. So you have to superimpose it on a analog wave. And let's say we have a sine waveform here. So this is a waveform where one, two, or couple of bits are superimposed. So this is called symbol. So this sinusoidal waveform is called a symbol. Now you want to transmit some bits. So you, for each bit of transmission, you should have a specific shape of uh, of the waveform. For example, if you remember our BPSK modulation that we saw in the previous lab, we were using 0 and 1 bit transmission, right? Again, the 0 1 sequence was there. When it was 0, we were using this kind of wave. But when we were transmitting one, we were using this symbol. So they were plus cause and minus cause, and they were totally reciprocal to each other. So the BP, for the BPSK, you can have this kind of scenario. For example, from the cause or from the sign, we can distinguish the 0 bit and the 1 bit. But sometimes when you need high data rate, I will just explain you the data rate later, but uh, first you have to understand what is the symbol. So for uh, the symbol can have different shape. For example, this is one shape, this is one shape, this is the other shape, for example. Then you have the third shape, which is like this, and then you have the one, two, three, and fourth shape, which is this. So it is like the same signal as this one, but it has half of the amplitude, so like that. So if you look at this one, it is something like cos of omega t plus 0, and this is for example sine omega t plus 0, and this is minus cos of omega t plus 0, uh, yeah, plus 0, and this is um, the same signal as this one, but minus zero point 0.5, or half of the cos of omega t plus 0. So let's say you have total four waveforms here. If you have four waveforms, then how much bits you can transmit? You can transmit, for example, you can transmit as much as 2 bits. For example, 0 0 here, 0 1 here, 1 0 on this wave, and 1 1 on this wave. If you need to transmit 4 bits, then what you have to do in that case, for 4-bit transmission, you need to have the waveform as much as 2 power 4, which is equal to 16. So you need to have 16 waveform, and then each waveform will carry 0 0 0 0 to finally 1 1 1 bit. Okay, and if you want to transmit 3 bits, then 2 power 3 is equal to 8. So in that case, you can transmit 3 bits per waveform, and you need 8 waveform for that one, right? So this is how the waveforms are created, and this is called the symbol. Each waveform is called the symbol, and each symbol is carrying some bits information. This is your information, and the information then this one, from here to the end, when the one cycle is completed, it is called the symbol duration. So what is the symbol duration here? If, for example, if it is 1 millisecond, it is completing its cycle in 1 millisecond, it means that the symbol rate is 1/1 millisecond. So it means that it is 1 kilobit per second. Okay, so it can transmit as much as 1 kbps. And then what will be the data rate? The data rate will be equal to symbol rate multiplied by bit per second. So how much is the symbol rate? Symbol rate is 1 kilo, which is 1000, multiplied by what, bit per second. So how much bits per second bit per symbol we are transmitting? Sir, that is not second, that is bit per symbol. We are transmitting 2. So it means that the data rate is 2 kbps, right? So in that case, if the duration is 1 millisecond, in that case the data rate is 2 kbps. Now to increase the data rate, you have to increase the waveform. To increase the waveform, more waveform will carry more bits per second, and then this thing will increase. This will increase, okay? And when that is increased, the data rate will also increase. Uh, but now the question is, uh, how much bits you can increase? Will there be any consequence if you are increasing the number of bits? For example, as I told you, BPSK is already there, and then you want to transmit 4 bit per second, like 4 bit, more than that, or 16 bits for per symbol or 18 bit per symbol. So yeah, you can create as many wave as you want, but if you are increasing the waveforms, then what will be the consequence, the ending consequence of that? So let me clear it, explain it further to you. If this is your real axis and this is your imaginary axis, okay, and if you are taking the example of bpsk, the previous one, the one we had seen earlier. So the data can be either this side, which is cos omega t plus 0 degree, or it can be either here, which is cos omega t plus 180 degree, right? So you want to further increase it. So to further increase it, it can be like cos omega t plus 90 degree, and here cos omega t plus 270 degree. Yeah, 270 degree. And if you, so you can increase the bits like that. And to further increase, for example, if you want to put it like here, 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 and here, it is making 45 degree almost, so it is cos omega t plus 45, and this is 90 plus 45 is 135, so omega t plus 135 of cos, and likewise this will be some other value and this will be some other value. And for further increasing it, then the angle will be further increased. So I can increase it like the uh, apparently we cannot see any problem here, but there are problems. If you look at this one, for example, if you have the BPSK case, BPSK case. Why I'm talking about the BPSK case? Because this is the most simplest one, and then I'll compare it with the most complicated one. So in the BPSK case, you have the bit interval defined here, and the other bit interval is defined here. So you are transmitting on the symbol which is here, and also you are transmitting on the symbol which is here. So at the transmitter, you transmitted it. Then there are lot of noise in the channel, and then at the receiver, you received it here. So when you received it, you might receive it like this and maybe like this. Then you, when you receive it, you can see that your bit was transmitted as this one. Okay, you don't know about how it was transmitted, but when you look at your signal which is received, you can say that how about how close is this to this axis? It might be close to this axis, which means that it is this one, and it should be close to this axis, which is this one. And it is BPSK, so you don't have to look for this one axis and also for this one axis, because it will be either at this axis, this one, or it will be at that one axis. So your signal will be easily estimated and it will be recovered. But what if your this signal moves from this axis to this axis? Then what will happen in that case? So when you are recovering it, then at the receiver side, you will see that it is very close to this axis. So maybe this signal belong to this part. So you will estimate this signal as like this one, but that will be completely wrong. And if your signal, which was supposed to be here and it moved, it shifted somehow like here, then you will be estimated at this position, which is completely wrong. It should be it was supposed to be here, right? So in that case, your signal completely get corrupted. And how it is completely get corrupted? By increasing the number of constellation, the number of, what are the constellation? Each constellation is the waveform. And what is the waveform? Each waveform is carrying your bits, right? So from here, now come back to this part. So as long as you are increasing your symbol, it means that you are also increasing the bits to be transmitted. But when you are increasing the bits to be transmitted, then there is more chance of your signal to get rotated to the other axis and get estimated wrongly at the receiver side. And when it get it estimated wrongly at the receiver side, it means that your data will there will be more chances of for your data to be corrupted, and your bit error rate chances will be increased, right? So this is all the concepts related to the modulation. And today in today's lab we will be covering two types of modulation. One is the BPSK, which is binary phase shift keying. And binary phase shift keying, we have seen that there will be two constellation, one at this position and the other at that position. And then we will consider a QAM, a very simplest form of a QAM. This is the real axis and this is the imaginary axis. So the real axis is usually called quadrature axis, and n phase, this one is called n phase axis in communication. So we will be seeing four QAM. Four QAM mean that each quadrant contain one of the constellation. So 4 quam is like that. If you are looking for 16 quam, 16 quam mean that there are four constellation per quadrant, right? So can you see from these two figures, from these three figures, in the first figure, if this one constellation move here or here or here or here, even further away from there, but the boundary line is here, so it can easily be estimated like, oh, it belongs to this part anyway. So there will be very less chances of the data for the data to be get corrupted. So the benefit is, the pros is low BER, bit error rate. What is the cons? The cons is low data rate, means the speed will be slow. So nowadays the people are looking for high speed internet, right? So when you are increasing the speed, then you have to pay for some other things. Then in that case, the bit error rate will increase. Why the bit error rate? This is the story behind that. And then if you look at this one, there might be a little more chances of error, because if this one constellation moved a little bit there, then the likelihood of this one, the estimation of this will be seem like it belongs to this one, and this will be at the receiver will be estimated that this constellation was here, and the bits will be recovered at wrong positions. And then here the situation get even worse. For example, if this one constellation moved there or this one moved here, then the story will be very different. The thing which was supposed to be here, that will be recovered at that position at the receiver, and likewise the same thing will happen here. So the data gets corrupted. The data is very prone to error and noises. So such kind of for example, noise or attenuation or the interference, they causes these kind of shifts. And I have already explained you that the noise, attenuation, and interference are coming from the various objects or various things in the environment. So the environment is not clean for the signal, wireless signal. There is always something, some degradation at the environment. So let's move to the main screen, and I'll explain you now from the slides. So firstly, the black interleaver. So the black interleaver is now quite clear. As I told you, the data at the input is coming in the sequential order, like x0, x1, x2, x3. So x0, x1, x2. So the data is coming in the row form, then the second row, then the third row, and then the fourth row. So the data is filled like this. Look at the pointer, like that. Okay, but at the column, the data is taken as x0, x3, x6, like this. The data is taken like that. First column, then the second column data, then the third column data, and so forth. So that is how the data, if this thing doesn't happen, then these 3 bits there, for example, you are sending the 3 bits and the deep fading occurs here, so all the 3 bits, the consecutive back to back 3 bits will be corrupted, and that is very worst situation. So in order to avoid that kind of situation, you are transmitting the data based on the column. So if the fading happens here, so that data is, those bits are not belonging to back, they are not very closely related. For example, the one bit is here, this is the fourth bit, this is the ninth bit, and this is the 10th bit. Sorry, not the, yeah, so they are far away from here, the zero, third bit, sixth bit, and ninth bit. But here it is the 0, 1, 2 bit, the 3, 4, 5 bits, the 6, 7, 8 bit, right? So in the interleaver, you are inputting, and you provide the input in the form of rows like this, and then you take the output like this, and then you transmit it. When you are receiving it, you will be taking the input in reciprocal way. So you will be taking it in the form of columns like that, and then you will be taking the output in the form of rows like that. So when you are taking the output in the form of rows, this input that you had feed it here at the transmitter side, it will be exactly equal to the output that you will get at the receiver side. So I hope this is quite clear now. And now let's move to the modulation part. So I already explained you what is the BPSK, what is the QQAM for constellation in each quadrant, and this is the N phase and this is the quadrature phase. I think I had put Q here, so that was wrong. Sorry for that. And then 16 QAM means that you have 4 symbols per quadrant. So 4 symbol per quadrant in the first, then in the second, then in the third, and also then finally in the last quadrant. So please remember that these concepts are more important than the coding, because in coding you will have, we have the ready-made functions and blocks and we use that, but behind those blocks all these concepts are working. So you have to be very clear about these concepts. If you have any question, you can ask me now, and then I'll proceed. And if you don't have question, then let me go to the MATLAB and start the coding. So I think it's clear for all of you. Now let's go to the MATLAB part. So I have simplified the code further. Previously, it was, there were more things, so I removed the unnecessary parts and I tried to make it more clear for you. So we are going to generate the 109 4 kilobits. So we are going to generate this much amount of bits here. So here in the MATLAB, you can see we generated that much of bits, and then we generated those bits in random form by using this command. And then why we use this one? We use the reshape command so that we make it 1024 form. Why 1024 form? Because it is 32 by 32 block. So 32 by 32 block requires at least 1024. So if your figure is not like that, if it is, for example, 3 cross 3 block, then you should have the input row coming in, the total row should, length should be equal to 9. So the 9 will be then interlude by 3 cross 3, right? But here we have like a big block size, 32 cross 32. So the input coming here should be at least, at length should be equal to 1024. So you provide the input here, which is the 4 rows, and all the 4 rows are of size this one, 1024. So we will reshape the bits here, and we will reshape it like that. So the length of whatever it is, so it will divide the length by that and then divide by 4, and then 4. And why are we dividing it by 4 bits? Because the we wanted our message to be equal to 4 bit per message. So the our message sequence will be equal to 4 bits, and that is the reason we are transmitting our source bit in the 4 bit stream, and then we are dividing it, and then we are just applying the Hamming coding. So previously I had used some parameters, so I have got rid of those things, and it's quite simple now. And then let's do today's part. So after that, we have to apply the block interleaver. So in the coding, it is very simple. Block interleaver. So the firstly, I'll just take the parameters from this thing, which is the linear coding, and I should say that size of linear coding is, for example, A2 B2. So when you are saying that what is the size of this one, it will show you that it has this much rows and this much columns. So A2 will store the number of rows and B2 will store the number of columns. Okay, so that is my uh, the size I got it from there. I always try to put the semicolon, because when you put the semicolon, it means that you will not be getting everything here on the command window. And then let's say I'm saying by linear is equal to uh, so there is a built-in command for doing the separation for the block interleaver. So I'll just choose the built-in and if you want to see it, it's like this uh, um, I think mat int or lv. So if you take this thing and simply Google it, for example, this one and MATLAB. So it will explain you everything about the matrix interleaver and whatever the mm, fields that are necessary there. So you need data, you need number of rows, and you need the information related to the number of columns. So all those things are coming here, and you can see further details by going to these details. So whenever you are not clear about any command, you can just Google it. Simply Google, go to the MathWork website, and from the MathWork website, you can just simply see all the details. Okay, so let's come back to the coding part. And then here, what is my input? My input is this one. So my input data is this one. And what should be the number of blocks? So as I told you, it is 32 cross 32 blocks. So it should be 32 comma 32. So 32 number of rows are there and the 32 number of columns are there. So that is done. So it was so simple in the coding, but yeah, please remember everything that is related to the uh, interleaver, block interleaver. Now we are done with the interleaving process, and it will take any row coming from the Hamming coding. It will take it as a row form, and then at the output, it will transmit it in the column wise. Okay, so that is the main idea of this part. And the purpose is to avoid any kind of errors that is happening because of the deep fading, and deep fading is leading to the burst noise. Now let's do the modulation. So modulation is also very simple. Firstly, we will be covering two types of modulation. So then I'll be giving you one assignment, and that assignment you will be increasing the modulation. Uh, Maybe I'll give you do you 16 quam by yourself, then give it to that block, do this changes to by yourself, and finally compute the bit error rate from your model and compare it with the bit error rate that from with my model, the model I have taught you. So then you should see the difference. So that kind of assignment I'll be giving you at the end. So if you have any question anywhere, you can please stop me right at that point and you can ask it. So BPSK modulation is the first one. And if you are not so clear about, even I used to do the same thing. And if I have to implement anything in the MATLAB, then I say that BPSK modulation and the MATLAB, and it will gives you the direction how to apply it. And here is are all the steps, are the necessary steps. I think I have got a chat question. Can you explain more? Ah, the question is, can you explain more about matrix interleaver? Matrix interleaver is actually equal to the block interleaver. So the block interleaver already I explained you. That is in the form of matrix. So you have certain rows and certain columns. The input should comes in the rows and the output should be taken from the columns. So it's actually in the form of matrix, and that is also called block. So the block interleaver and the matrix interleaver, they're almost the same terms. So if you have to use this BPSK modulation, all these informations are here, and yeah, the way how to apply it. So everything is here. So you can simply Google everything, and yeah, Google is your best advisor. It will recommend you what to use and how to use. So for the BPSK modulation, as we saw in that Google page, the network page. So let's say I'm calling the H1, and firstly I should make a function from the class, the BPSK function from the class, and it is com dot. I think I should copy it from there. So com dot BPSK modulation. Just copy it and just paste it. So if you just run it, oh sorry, editor. If you just run it, H1 is here. So H1 will uh, produce the that kind of function for you. You have zero phase offset, and if you want to provide the phase offset as well, then you have to put it in the input argument. Okay, so that is uh, created now, and now your bits are, for example, I'm calling it mod bits is equal to the output of this one. So if we see the this one, sorry, let me show you like that. It's like that. Okay, so it is the number of rows are 1024 1 kilo, and the number of columns are 7. uh, I want to show it in different way. I want to show it like 7 cross 1024. Why? Because I'll tell you the reason when I apply the modulation. But I want this part to belonging to our first sequence that we transmitted, the second sequence we transmitted, third sequence. So column by column we can easily separate it out. Even with this one it's possible, but this one will require, this function require column input. So for that we will just take this one input, we will, and we will take the transpose of it. So you know the transpose, right? And the matrix transpose transforms the number of rows to the number of columns and the number of columns to the number of rows. So it just rotate the matrix. And when you run this one, now let me show you both. This is mod bit, right? So you have as much as 1024, okay, the total number, and each one is containing this one. This is, for example, the first message you transmitted. So the Hem encoding was taking 4 input and it was taking 3 parity bits with that. And then the second one was here, then third one, fourth one. So now you can easily see which one is your which one message, right? And the total messages were almost 1 kilo. So in total you have 7 kilo. Why 7 kilo? Because 3 parity bits were added from the Hem encoding. The actual were 4 kilo. Now it's already, and now let's make a for loop because we have multiple rows there. So I is equal to 1 colon length of, sorry, length of length, yeah, this one, and end it here, and let's write everything inside the for body. I'm calling it mod linear is equal to h1, which is this function, and I want to apply this bpsk function on what? So I want to apply the bpsk function on the this data, and this data is column wise, so I comma column, right? And I think I should also save it here. um, so comma colon I. Yeah, I think you should, by yourself you should see this, how this thing is working. It's not that complicated, it's just simple MATLAB command. So it will run up to the length of this mod bits, which is here, and then it will save the answers here, and it will meanwhile apply the BPSK modulation to the embeds, which is the input bits, right? So I'll just run it. I think there is error, and yeah, I think let me take this one, take it here, and take the transpose here. What is the error otherwise? Oh, it's not, it is this one, sorry. It is not semicolon, it is colon. Okay, I think it should be okay. And unrecognized length, so the length spelling is wrong. Length. Okay, now it's clear now. And yeah, and I want to see how does this thing looks like. So I can see it in the scatter plot. In the scatter plot, I can simply see one row of this one because there are multiple rows. So I want to see only one of that. One column, sorry, it is column wise. So if you look at like that, here is your BPSK data, and I want to put it like this. I will say that this is BPSK because I'm also applying the um, other one, QAM, so they should be both looking different. So you can see, I think it's so small. Let me make it a bit bigger. So let's say this is 4, and I want to express it in this form, so it will be now visible. So you can see the first constellation is at 0 position, and then the second constellation is here, right? So this is the BPSK. So one of my constellation is shown here and the other constellation is shown there. But at the receiver side, because of the those factors, as I explained you, the attenuations, the interference, and the noise, they may get rotated. Okay, so even if they get rotated, they have a lot of space here, right? Even till this part, if they are rotated, they still belongs to here because the boundary line is this one. And even this one, if get rotated, they will still belongs to this part. So let's move forward to the um, other part, which is the 2 number is the 4 QAM. 4 QAM modulation, and that is far simplest than the first one. So I will say for I is equal to, I think I should just copy this part, Control C and then Control V. Yeah, uh, I don't have to write everything from the scratch. And length of bits, that is fine. And instead of this one, I should just write for QAM, and then R simply small QAM. Maybe the capital might be a keyword. so I don't want to do that. And then there is this function, QAM modulation. So if you want to further confirm it, you can just go to the QAM mode MATLAB, and it will show you quadrature amplitude modulation. So this is the for it is used for the QAM, and you can also the symbol order, you can put it order, you want to do it 4 QAM, 16 QAM, 32 QAM. So you simply need to increase this number, and based on that it will be also increased. So this is my input, and furthermore I want to um, make it 4 QAM, and that is it. Yeah, that's done. So the 4 QAM is already applied here, and now I have two inputs. One is the BPSK and the other is the 4 QAM. Okay, if you want to make it 16 QAM, and then you can run it, and then you can see this one, and 16 QAM, it should be, yeah, anyway, it was in, yeah, it should be different. See, it has a different range because you have constellation spread over the first quadrant, 4 constellation in each quadrant. So that's why you can see the figure in +3 and 1 and something like that. Okay, so we are not covering this one. We are only keeping it to the 4 QAM and also to the BPSK modulation. So I hope all these things are clear. Including this part, FEC part, then the block interleaver, all the information that I gave you related to the block interleaver, and also the modulation. So for the modulation, we have used the BPSK. Now I hope you clearly understood what is the BPSK, and also we use the 4 QAM. So that is it for today. And yeah, I think this was our objective, BPSK and 4 QAM. So you have to do some changes, make some changes. As I told you, you can make it 16 QAM or some other thing, make the changes in the block. This is how you can learn. For example, you can make it 16 cross 16. If you want to make it 16 cross 16, then what should be the input here? So if you multiply 16 cross 16, 16 cross 16, 256. So the input should be 256. Then how can you generate the 256 here? And then how you can manage it with the matrix reshaping? So can you just do that kind of experiments? Yeah, just make some changes in the code and uh, make the code align to your own purpose, and then just implement it, and let's see it's working or not. So if you have any question or any concern related to this one, you can simply ask me through email. You can send me the snapshot. So do you have the question? If you have any question, you can ask. Uh, Otherwise, you can leave. I'll Is there anyone who came late for the
1540, please.
okay, 1540? 1540. 1540. Yeah. Okay. Late or in time? When did you come?
I'm late.
Okay. Thank you. Anyone else? Anyone who came late?
0613.
Okay. One. Sorry. 130613. Okay. So you were also late? And
Yes.
okay. Anyone else? Okay. So I think it's fine. Yeah. Okay. So that's all for today. And I'll see you in the next lab. Thank you all.
Thank you.
Thank you.
Thank you.
You.
Thank you.